Hello guys, I'm Professor Mihir Bhatt and I am going to take the presentation on the breakdown mechanisms in solid dielectrics. So today our agenda is to learn about how the conduction and breakdown has been taken place in the solid dielectric materials. So here you can see the photographs which guide you the applications of the solid dielectrics. Okay, like in the transformers, you can also see the solid dielectrics in the form of the bushings, line insulators. Okay, you can also found them in the circuit breakers, small transformers, large transformers. So in any of the high voltage devices, you always found the presence of the solid dielectric materials. So before proceeding to the conduction and the breakdown, it is required to know some basic facts related to the solid dielectric materials. Then we should know about what sort of the properties that solid dielectrics should have, and at the end we will touch upon the various breakdown mechanisms observed in solid dielectrics. So let me show you some photographs. Okay, here you found their application in transformers, not uh, at the outer side but internal to the transformers. You also find the presence of the solid dielectrics like the press board. Okay, which is used to insulate the high voltage, low voltage windings, and low voltage winding with the core. Okay, then you may found the impregnated paper between the two turns of the same winding. Okay, in circuit breakers. Okay, the transmission lines. Okay, various types are there. Either you can go with the porcelain type or the ceramic type or the glass type or the silicone rubber type. Okay, there are a lot many of the options are available. That depends upon the magnitude of the voltage stress and all. Okay, for the low transmission lines. Okay, so bushings. Okay, so here I have represented some sort of applications of these solid dielectric materials, which in general you can see through your eyes. So solid dielectrics. So solid dielectric materials, as you know, that it is used in all kinds of electrical circuits and devices to insulate the one current carrying part from the another when they are operating at a different voltages. So this statement is best suited to the transformers where the low voltage winding and high voltage windings are isolated by this uh, synthetic resin bonded paper kind of the press board. Okay, so SRBP, usually known, which is used as a solid dielectric to insulate the low voltage winding and the high voltage winding. If we are taking the case of the transmission line insulators, then the transmission line insulators not only provide the insulation between the current carrying conductor and the transmission line tower, but it also provides a mechanical kind of support. So solid dielectric materials are not only for the purpose of giving the insulation, but they are also acting as a kind of a mechanical support. Okay, so if they are internally applied, then we can correlate them with our bonds. Okay, so bonds are generally there to support our entire body. Okay, as well as you can also found the applications of that muscles and everything. Okay, so muscles and these bones. Okay, so ultimately that structure will give better support to our body. So similarly we can also say the solid dielectrics are one type of the bonds to those high voltage devices to provide the mechanical supports. The solid insulation, okay, as I have said, that it not only provides the insulation to the light parts, but it sometimes also provides a mechanical support to the equipment as well. So we need to think of its properties. See, whenever we are discussing any kind of the dielectric materials and likely to apply in any high voltage equipments, first we should understand about its basic properties. So few of the properties are normally seen very similar to those gases and the liquids. Okay, so as we need to use these solid dielectrics to fulfill the requirement for isolation purpose, so it should have the very high dielectric strength. Okay, it should have high mechanical strength so that it can provide better mechanical support to the equipments. It should have a low dielectric losses. It should be free from the moisture. It should be free from the internal defects like cavity, gaseous inclusions like voids and cracks, etc. So when we are selecting any solid dielectric materials, first we need to accurately define or accurately understand about its all properties. So various types of testings needs to be conducted to determine the quality of the solid dielectric materials by determining the shown properties. Okay, so it should be resistant to thermal and chemical deterioration as well. So the processes responsible for the breakdown of gases, okay, are usually governed by the rapid growth of current due to emission of electrons from the cathode, ionization of the gas particles, and the fast development of avalanche processes. Okay, so these are the normal conduction and breakdown mechanisms usually seen in the gaseous dielectrics. Okay, whereas in case of the solid dielectric materials, when the breakdown takes place, the solid get permanently damaged, whereas gases fully and liquid partly recover the dielectric strength when the electric field is removed. So in case of the solid dielectric materials, the breakdown may occur over the surface, so that is known as a flashover. So in that cases, there might be some damaging effects of the spark that we can usually see on the occurrence of the spark. So that phenomena is known as a flashover. It doesn't mean that the insulator, the solid dielectric material, is completely damaged. But if the tremendous voltage stress was being applied to the dielectric material, and if the breakdown takes place through the dielectric, then it is known as a puncture phenomena. Okay, and the puncture itself indicates a permanent damage. So phenomena is like similar to the puncture that happens to the cycles tire or the tire of the cars and the motorbikes. Okay, you have observed when the puncture happens. Okay, you need to take the immediate action, otherwise it will cause the permanent damage to those tires. But here the insulator is made up of a solid material, so if the puncture takes place, it means it will permanently damage. So in those cases we need to replace the solid dielectric. Okay, we cannot reuse it, whereas in case of the gases, if we remove the applied voltage source, then it will keys the ionization process to zero. As a result, the arc gets disappear and the gases has the tendency to recover its dielectric properties back to the normal state. Whereas in case of the liquid, there always be the carbonization. So as a result, the liquid dielectric partly recover its dielectric property. Whereas in case of the solid dielectrics, if the puncture happens, then it is permanently destroyed. So breakdown of solid dielectrics not only depends upon the magnitude of the applied voltage, but it also depends upon the time of application of voltage. Okay, so depending upon this time, there are so many mechanisms usually seen with this solid dielectrics. So factors that generally affects the dielectric strength of solids are the first temperature, second is of course its mechanical strength, impurities or cavities, gaseous inclusions, water particles or moisture, and permittivity. So these are the factors which entirely governs the dielectric strength of the solids. Okay, the chemical deterioration as well. So breakdown mechanisms actually a very complex phenomena in the dielectric materials, and it usually varies with respect to the time. Okay, so depending upon this time variation, the mechanisms of failure observed in solid dielectrics are classified into this category. So if you look at to this characteristic, if you look at to this characteristic, the breakdown voltage varies with respect to the time. So here you can see, if suppose I want to observe this intrinsic or electromechanical breakdown, then what it needs? It needs higher magnitude of the voltage with a lower time. So if the breakdown of the solid takes place in a very short duration under the impact of the high potential magnitude, then the breakdown is known as either the intrinsic breakdown or the electromechanical breakdown. So as the time goes, the breakdown happens even at the lower potential. So this characteristic generally represents the aging phenomena of the solid dielectric. So one is the intrinsic breakdown, that is ionic breakdown, second is electromechanical breakdown, third is breakdown due to traying and packing, then thermal breakdown, then chemical and electrochemical breakdown, and breakdown due to internal discharges. So these are the breakdown mechanisms which are normally observed in the solid dielectrics when they are subjected to a higher voltage. But again, the mechanism of failure depends upon the time of application of the voltage and the magnitude of the applied voltage. So if I am applying the lower potential, then I cannot achieve the intrinsic, electromechanical or the avalanche breakdown, but usually it may produce the thermal breakdown or the electrochemical breakdown. Okay, or the uh, breakdown due to the internal discharges if it contains the internal impurities. So we will see it later on. So let us start with the intrinsic breakdown. So when the voltages are applied for a very short duration, okay, you have seen that characteristic. Okay, so on x-axis there is the time, and on the y-axis there is the voltage. So when the voltage is applied are very high for a very short duration, so this one. Okay, so this is the region where I can observe the intrinsic breakdown. So when the voltages are applied only for very short durations, the dielectric strength of solid dielectric increases very rapidly to an upper limit, which is known as intrinsic electric strength. Okay, so up to the point of intrinsic electric strength, the dielectric material has capacity to withstand the applied voltage. But when the voltage across it becomes more than its withstanding capacity, instantly the material gets collapse. Okay, so the intrinsic strength normally defines the withstanding capacity, the electrical stress withstanding capacity of a given dielectric material when a very high magnitude of voltage for a very short duration is being applied. So intrinsic breakdown depends upon the presence of the free electrons which are capable to migrate through the lattice of the dielectric. Okay, so intrinsic breakdown usually depends upon the presence of the free electrons. So generally the fewer number of electrons are always present into its conduction state. So when the voltage is being applied, they will be now jump from their valence band to the conduction band. So usually the small number of conduction electrons are present. Why? Because of some structural imperfections and small amount of impurities. So the impurity atoms or the molecules or both are acting as a trap for the conduction electron up to the certain range of electric field and the temperature. So whatever the imperfections are there or whatever the impurities are present, they will try to prevent the jumping of electron from its valence band to the conduction band. Okay, so they are actually trying to block them, okay, up to the certain range of the electric fields and the temperatures. So when this range gets exceeded, the additional electrons in addition to the trapped electrons are getting released, okay, and whatever the electrons are now there will participate in the conduction process, which is usually known as the ionization of the solid dielectric. Okay, so to observe the conduction phenomena, it is needed a minimum energy which can dislodge the electron from the lattice of the solid structures. So to obtain the intrinsic dielectric strength of material, the samples are so prepared that there is high stress in the center of specimen and much of the lower stress at the corners. So you can see them in the figure. Okay, here you can see that the force, the maximum force is being applied exactly to the center just to determine its intrinsic strength. Whereas as I am moving from center to the right side or center to the lower side, the stress is gradually reduced. So this is the low stressed region. Okay, whereas the highest stress is applied at the center point of the given dielectric material to determine its intrinsic dielectric strength. So there are the two types of intrinsic breakdown. Number one is electronic breakdown. Okay, the electronic breakdown means when the applied electric field is higher, the electrons will gain a sufficient kinetic energy from the electric field and crosses the forbidden energy gap from the valence band to the conduction band. Okay, so initially when there is no stress, everything is superb, but when the applied electric field is higher, then the electrons are getting excited. As a result, they will gain the kinetic energy from the applied field and cross the forbidden energy gap from its valence band to the conduction band. So when this process is repeated, it will allow to produce more and more electrons. Okay, so eventually as the number of electrons are going to be multiplied, it will lead to the complete failure. Okay, so here the breakdown is taking place because of the electron multiplication. Okay, so because of these electrons, the mechanism of failure is known as the electronic breakdown. Second is the avalanche or the streamer breakdown. So this streamer breakdown in solid dielectric is quite similar to the breakdown in gases, which you can observe due to the cumulative ionization process. So conduction electron gains the sufficient energy above a certain critical electric field and causes the liberation of electrons from the lattice atoms by the process of ionization by collision. So under the uniform field gap condition, if the electrodes are embedded in the specimen, the breakdown will occur when electron avalanche breathe the electrode gap. Okay, so there is the uniform distribution, but if the strongly non-uniform gap is there, then the electrons are distributed non-uniformly, which you can see into this photograph. Okay, so eventually how it distributed like this. Okay, so this is the avalanche of the electrons, which produces the avalanche breakdown. So here it will represent the non-uniform distribution of the electrons. Okay, so it will try to ionize the greater region or the greater part of the dielectric materials, and successively enhances the field at the low stressed region. Okay, and at the end, once they breathe the gap between the two electrodes, the complete spark is being observed. Second is the electromechanical breakdown. So electromechanical breakdown means when the dielectric material is subjected to the electrical field, the charges of opposite nature are induced on the two opposite surfaces. Okay, on the two opposite surfaces of the material. So the force of attraction is developed. Let us consider a simple case. Okay, here there is a solid dielectric material. Suppose this electrode is let us say the ground or the negatively charged, and this electrode is under the stress of the higher voltage. Okay, so now as it simply represents the capacitor. Okay, so when we are giving the voltage, the surfaces of the electrode will gains the charges of unequal polarities. So here there is an action of the Coulomb. Okay, so according to the law of the Coulomb, there is a force of attraction observed between these two metallic conductors. So this force of attraction will try to press the material, Okay, so here the dielectric material experiences the electrostatic compressive stress. Why the electrostatic compressive stress? Because there is a force of attraction between this positive charge is collected at one electrode and negative charge is collected at the other electrode. So according to the law of the Coulomb, there is a force of the attraction, and this force of the attraction will try to press this solid dielectric. So that force is known as the electrostatic compressive stress. And when this electrostatic compressive stress becomes higher than the mechanical withstanding capacity of solid dielectric, the material gets permanently damaged. Okay, so if the initial thickness, if we are assuming that the initial thickness, okay, suppose this is the thickness of the solid dielectric, initial thickness is supposed to be d0. Okay, and this thickness is compressed to a thickness of d under the applied voltage. So when I am giving the voltage, the electrode gets compressed, so there is a change in the thickness of the dielectric. So suppose this is the thickness of the solid dielectrics under the application of the high voltage stress. Okay, so the compressive stress developed due to this electric field is given by F is equal to 1 by 2 epsilon 0 epsilon r V square upon D square. Okay, now as we know that the uh, materials, okay, the materials have the Young's modulus, okay, the modulus of elasticity, you can say. So if we are considering the Young's modulus, then the mechanical compressive strength is given by gamma times ln d0 upon d. So if we are equating both the terms under the equilibrium condition, then 1 by 2 epsilon 0 epsilon r v square upon d square is equal to gamma times ln d by d0. So it will give us v square is equal to, if we simplify this equation, then it will give us v square is equal to d square into 2 gamma upon epsilon 0 epsilon r ln d0 upon d, which is further simplified to this form, k d square into ln d0 upon d. So differentiating that equation with respect to d and equate it to 0, we will get this equation 2v dv upon d of d is equal to k into 2d ln d0 by d minus d square into d by d0 into d0 by d square, and we are equating it to the 0 value. So we can by solving the equation uh, we can get this mode of condition, that d upon d0 is equal to 0.26 sorry 0.6 for this equation, if you are assuming that if you are solving this entire equation, okay, because we have equated to 0. Okay, so 2d ln d0 by d is equal to d. So finally we can get one sort of the condition, that d is equal to 60% of d0. It means that for any real value of the voltage, the reduction in thickness of the specimen cannot be more than 40%. Okay, d0 indicates the initial thickness, okay, when there is no compressive stress, and d represents the thickness achieved by the solid dielectric or the specimen when it is subjected to the high potential. Okay, so because of that compressive stress, the thickness achieved by the solid dielectric is 60% of the initial value. Okay, so for any real value of voltage V, the reduction in thickness which is observed is not more than 40%. So there is a 40% of reduction. So if the ratio V upon D, that is the electric field intensity, and this value of V is less than the intrinsic strength of the specimen, a further increase in V shall make the thickness unstable and the specimen gets collapse. Okay, so ultimately if the magnitude of the applied voltage is unable to further uh, press the material, then we cannot observe the damaging effect to the solid dielectric. But if suppose the voltage is tremendously large and more than its intrinsic strength, then the material gets collapsed. So highest apparent strength is obtained by substituting the d is equal to 0.6 d0. So we have this relationship. Okay, V upon d0 is indicating the electric field intensity. So 0.6 into gamma upon epsilon 0 epsilon r raised to 1 by 2. Okay, so it will approximate only that it will highly dependent upon the gamma. The other is the thermal breakdown phenomena. Okay, very simple mechanism to understand. So when we are giving the electric field, ultimately when we are giving the voltage to a dielectric material, the conduction current is always be flowing through the material. Okay, there always be the flow of the conduction current when it is subjected to the voltage stress. So what this current exactly doing? This current will heat up the specimen and raises the temperature of the specimen. Then once the heat is generated, it will be transferred to the surrounding medium by the conduction through the solid dielectric and by the radiation from its outer surface. So once the heat is produced, there are the basically three processes. One is the conduction, then whatever the heat has been conducted is then convected towards the surface of the solid dielectrics, and from the surface of solid dielectric the heat is radiated out. Okay, so in general way we can say that there is the heat generation and the heat lost. So equilibrium is reached when the heat used to raise the temperature of dielectric plus the heat radiated out becomes equals to the heat generated. Okay, the heat used to raise the temperature of the dielectric, it means it represents the convection phenomena, plus the heat radiated out means the heat which is radiated from the surface of the solid dielectrics into the surrounding region is equals to the heat generated. Okay, so when this situation is happen, we can say it is in a equilibrium condition. So heat generated in a solid dielectric depends upon the type of applied stress. So heat generated under DC stress is calculated from this equation. WDC is equal to E square sigma watt per centimeter cube, and when it is subjected to AC stress, it will be calculated from this formula. WAC is equal to E square F epsilon R 10 delta upon 1.8 into 10 raised to 12 watt per centimeter cube, where E represents the magnitude of the applied voltage, F represents the frequency of supply, epsilon R represents the relative permittivity of dielectric, and 10 delta represents the dissipation factor. So generally the breakdown will take place when the heat generation becomes more than the heat dissipation. Okay, so here there are the two possibilities. One is for E1 and second case for is E2. Okay, so this inclined line, okay, this slanting line represents the heat lost, and these curves E1 and E2 represents heat generated. Okay, so here now you can see for this first case, the heat generation is lower than the heat lost, so breakdown is not possible. Whereas in case of the E2, as you can see that the heat generation, this curve, the heat generation in the region of TA to TB is more than the heat lost. So when the heat generation becomes more than the heat lost, the breakdown will take place, and that breakdown is known as a thermal breakdown. Okay, so if we are considering this type of voltage, type of the applied voltage, then you can see that if we are applying DC stress, then heat generation becomes on the magnitude of applied voltage and electrical conductivity of the solid dielectric. But in case of the AC stress, it will depends upon the magnitude of applied voltage, frequency of the supply, relative permittivity, and the tan delta value. Okay, so in case of the AC stresses, in case of the AC stresses, the heat generation is somewhat more as compared to the heat which is generated under application of DC stress, because in case of the AC there is a frequency, so you can see that the heat generation is proportional to the frequency of the supply. Okay, so as the frequency increases, the amount of heat generation is also increases. Okay, so the lower amount of stress is uh, stresses can produce the thermal breakdown in solid dielectric compared with the DC stress. The next is chemical and electrochemical breakdown. So chemical breakdown, it means that when the equipment is not in the service. Okay, now as the suppose if we are taking the case of the transformers, and the transformer consumes the liquid dielectrics as well as the solid dielectrics and the composite dielectric. So if the transformer is not in a service over a longer time, then it will always create a chemical reactions between these chemically formulated insulations. Electrochemical breakdown, it means that the chemical reactions taking place between two dissimilar kind of the dielectric materials when there is an application of electrical supply. So in the presence of air and the other gases, some of the dielectric materials always undergo the chemical changes when they are subjected to the continuous electrical stresses. So one process that we could observe is the oxidation process, and this oxidation process will develop the surface crack in the presence of the oxygen. Second is hydrolysis process, which takes place in the presence of moisture and the water content in the dielectric. So it will reduce both the electrical and mechanical properties. Third is the chemical reactions, okay, in the absence of the electric field. So progressive chemical degradation of insulating material can occur due to the chemical instability at high temperatures, oxidation and cracking in the presence of air and ozone gas, hydrolysis due to moisture and heat. The chemical reactions occur between the various insulating material which lead to reduction in electrical and mechanical strands, which will result ultimately in the failure. So these are the possible reasons to uh, produce the breakdown due to the chemical reactions under the presence of electric field or under the absence of electric field. So oxidation process normally observed if the gas content is found, if suppose oxygen is present. The hydrolysis process usually found if the solid dielectric consists of the moisture or the water content. Okay, so because of the imperfections, usually this kind of the phenomena normally seen, but but at a prolonged operation of the solid dielectrics. Okay, so generally the electrochemical failures or the chemical failure usually occur at the lower voltage when it is being applied over a longer time. So it is a slow process. Okay, it is a slow process. So in the next lecture we will see the how the breakdown will takes place due to this string and tracking, and how the breakdown will takes place due to the internal discharges. Okay, so thank you.